Good afternoon, good evening, wherever you're joining in from. Welcome to another live session at the Reactors. My name is Rav, and I'm the program manager at Reactor London. Before we get into the session, please take a moment to read our code of conduct. We're all here to learn, so please be respectful of other people's views, understanding of differences, and please be kind and considerate in the way you engage. The chat will be open throughout, and we do encourage you all to participate. Today, we have a very exciting event, which we have collaborated with a company called NannyML. And this event will be led by Wojtek. I hope I pronounced the name right. But with that, I'm now going to bring him up on the screen, who will lead the session. Hello.
Hey, Raf, how are you?
Good. I'm now going to, the stage is all yours. So I have added your screen. If you need me, just shout. I'll be in the background.
Perfect. I'll just do a quick check. All right. So welcome, everyone. And today we're going to talk about detecting silent machine learning model failure. So basically, what can happen with your models when they are deployed to production? How can we detect any issues? And then how can we troubleshoot them and resolve them? So it can serve as kind of an introduction to machine learning monitoring. So let's get started with the agenda. So first, we're going to define two biggest reasons why machine learning models can fail after they have been deployed, and these reasons are data drift and concept drift. We'll define what they are and how they can potentially impact performance. Then we're going to cover the topic of performance and why most often in production we don't have access to the target data, so we cannot simply calculate performance. Instead, we should estimate. And then we're going to cover kind of a high-level intuition of an algorithm that we developed that allows you to estimate the performance of your machine learning models, even if you do not have access to the ground truth. And then after we've done that, we know whether our machine learning models are performing well or not. We're going to come back to data and concept drift, and we're going to talk about the techniques that we can use to detect those, to kind of troubleshoot and find what are the potential reasons why our models are not performing well. So we have a kind of a starting point in resolving those issues and making sure that the value that our models are providing is protected. And before we jump into that, let's set the stage with a typical use case that I will be referring to throughout the presentation, that you can see basically in any bank currently, when it's about detecting loan defaults. So what we have is we have credit scores, we have customer information as our model input, so as our features, and we're trying to predict whether a person is going to default on a loan or not. Our target here specifically, we just assume it's going to be non-payment within 1 year. So we'll have to wait an entire year before we know whether our prediction was correct or not. And we're going to use technical metric to evaluate the quality, so the performance of the model. This is what I'll be referring to as performance. And here, as an example, we can use a ROC AUC, which is a very typical metric for binary classification tasks such as loan default prediction. So now let's get started with data drift and concept drift. And here, what you see is kind of high-level idea of what you're actually trying to do when you train a machine learning model. There exists a pattern in reality, the true pattern that actually is in the, not in the data, but actually in reality. And here we have an example where there's one feature, one of the input X, and we're trying to predict based on X negative or positive class. So the simplest possible binary classification. And we see that as X increases, it is more and more likely that a given data point is going to belong to a negative class. Then what happens is we gather the data in one way or the other. Maybe we just record what has been happening in the past, maybe whether the people paid back the loans or not. So we'll have to sample from reality. It's not going to be the entire population of all our potential future customers, but it's going to be just and current customers. It's going to be some sample. Then this is really the data that we get as data scientists to work with. So maybe we'll split it in our training, validation, testing set. We'll do some algorithm development there, and we have a model that we think works reasonably well. And we tested that on our unseen data that we set aside, so everything seems fine. And now, as we deploy the model, these things can change. True pattern can change, and sampling can change. And let's evaluate what happens if they do change. So first, let's talk about the data drift. Data drift is a change in the sampling mechanism. So the true pattern that exists in reality remains unchanged. There's the mapping between the model inputs, and the target remains exactly the same. But what changes is how the data distributions look like. So we can talk about data drift being changed in the model inputs. And of course, from that, we will also get the change in the model outputs, assuming that the model doesn't change, just because you have to. So we'll see that the data as we had it is actually different. So we see that even though the real distribution, the underlying pattern is still the same, we will see that our distributions of the model input data are actually different. And also the class balance might significantly change, because maybe we're sampling now from a region when there's more positive or more negative class than before. And just to fully define data drift in a more formal way, you could consider it, or you can define it as a change in joint model input distribution. So the probability of X of model inputs. And if there is data drift in our use case, it might lead to drop in performance, but it's not necessary. To give you a few examples, imagine that that there is strong data drift when most of your data used to be in a region, when most of the data points belong to negative class, and it was a very easy problem. There were just very few points in a positive class, and then the data is going to shift to a slightly different region when it's still mostly negative class. There's only a few data points in positive class, and the problem is equally simple to solve. If the model had enough data points to learn on both regions, that kind of data drift will not impact the performance of the model significantly. However, of course, we can also see changes in data drift, changes in data, so data drift that will significantly impact performance. And to give you an example here, imagine that we go from regions where the data is very easily separable to regions that are close to the class boundary. Then we would expect that the model will behave worse, will perform worse, just because it's a harder problem to really distinguish between the positive and the negative class. So you can imagine, to give you a very specific example, that we can have very rich old people that take loans. If they take loans, they are quite likely to pay it back. The risk of default is very low. And then if they move to another region, maybe it's younger people that are even richer, it's also quite likely that they will pay back the loan. But if we go to maybe people more in the middle class, or people who are for some reason more prone to risky behavior, it's much harder to tell whether they will pay back the loan or not. So in that case, if we see that kind of data drift, we would expect a drop in performance. Now, let's cover the second main reason why your model might fail in production, or where performance may deteriorate, and this is the concept drift. In that case, what changes is the true pattern. So something, if we have pure concept drift, will remain unchanged, and the true pattern changes. So the either causal or just some kind of non-causal relationship between your model inputs and the target changes. Maybe it used to be that increasing X led to some slow linear increase in the negative class likelihood, and now we see it's much stronger. It looks much more like sigmoid. Or maybe their relationship would be completely inverse. These are all examples of concept drift. And now we see that even though the sampling remains the same, and then our model inputs will remain roughly the same, what will change is the target distribution. And there's a huge difference here, is that the prediction distributions will not change under pure concept drift, because the model has no way of knowing that the concept is different now, because it has been trained on the past data. What will change, however, is the target distribution. So we will have label drift, but not prediction drift here. And as you can imagine, if there is concept drift, that means that the pattern that was learned by the model is no longer fully relevant or fully accurate, or as accurate as it used to be. So we will see most likely significant degradation in performance. And let's again define it a bit more formally. So then here we can see that the concept drift is the change in the underlying concept or pattern or mapping between the target and the model input. So it's a probability of Y given X, so given the model inputs, given the features. And you can visualize it here in slightly easier maybe way to digest. Instead of looking at change in the distribution and the underlying patterns, we could just look at change in true class boundary. So again, here I'm not referring to the class boundary that's found by your model, because that will remain the same as long as you don't retrain your model, but change in the true class boundary. If we train our model on the data on the left, we'll have a class boundary kind of like that. And then if we see very strong concept drift, that kind of concept drift is rare, but it might happen. For example, with customer analytics during COVID, we would see that the pattern is completely different. So our model, of course, will make a lot of bad decisions. So we have these two main reasons. And now let's move on to the second part of the presentation when we talk about the performance. So first of all, why performance matters, why it's something we should really pay attention to. Why can't we just look at, oh, there's data drift, something has changed. Yes, but that doesn't mean that you need to be worried. And things change all the time. If you have a model with 200 features, there's going to be always some kind of data drift within every feature. And it might even be statistically significant, but it won't really impact the performance of your models, because especially modern machine learning algorithms are quite robust and can handle data drift within certain regions and within certain limits quite well. So just tracking performance drift actually data drift doesn't tell us really anything about the performance drop, because you might have performance drop even if there's no data drift, which is a very bad kind of case. But what's much more likely is you will have data drift and you will see no performance drop or very small performance drop. Another reason why we should focus on performance is that it's something that we simply optimize for in training. We pick our metric, whether it's in classification F1 or ROC AUC or some other metric like accuracy, or in case of regression, we could look at mean absolute error and metrics like that. We optimize that in training because it is the best proxy we have from the kind of data science side on the business impact. And when we develop machine learning models, what we want in the end is to drive as much impact to the organization that we're developing the model for. And ideally, we would track this business impact directly, but this, if possible, we should absolutely do it, but it's rarely possible, as there normally follows a complex chain of decisions from the output of machine learning model to the business impact, and it's impossible to really link those two in a very direct way. So yeah, performance matters. And now, why can't we just calculate it? Because we normally don't have the ground truth. And why is that? So coming back to my example, we can see that in case of these loan defaults, we'll have to wait an entire year before we can just simply calculate whether a person that we've given a loan to is going to default or not, or has defaulted or not. And that means that we might be operating a model that's actually really bad and went from generating value to actually creating unnecessary risk and losing money per loan, because we might go from positive ROI per loan to negative ROI per loan if we start mispricing risks really badly. And this risk tends to be unacceptable, especially in high impact use cases like credit, like loan default prediction. So we don't have a ground truth there. Then another thing is that even when we get the labels after a year, we still don't have full labels. What I mean by that is, for every person we decided to give the loan to, we will know whether they pay back the loan or not. However, for every person that we decided to not give the loan to, we will never really know whether they would have paid back the loans or not if they were given it. So the labels are incomplete, so we cannot fully compute the confusion matrix here, because we don't know whether our negatives are false or true. And there is another kind of family of use cases that are called automation use cases, when we're trying to automate human labor, such as image captioning, text summarization, text classification, document classification, things like that, and pricing, where we actually never know whether the prediction was correct or not, because to know it for all the data points, we would need to have humans redo the exact same things that we just automated, which would defeat the purpose of the use case. So there we could do some kind of spot checks, and we will double check with humans, maybe 1, 3, 5% of the data, and for those we will have the actual ground truth, so we'll be able to calculate performance. But still, for vast majority of the data and basically all automation use cases, we will never get ground truth, so we'll never be able to simply calculate performance. So we need to estimate it. And how do we do it? So here I'm going to give you a high-level kind of intuition behind the algorithm that we developed at NannyML. And as far as I know, we are currently the only company, at least the only open source library that offers any kind of way to estimate performance of a model that's deployed in production without access to ground truth. So what we will do is we will look at the impact of data drift on performance. So we are assuming that there's no concept drift. If there's concept drift, we cannot really estimate performance very well. So we're assuming that there is no concept drift and there's just data drift. And we will look at the regions in the model input space. And here you can see on the in the picture on the left, you will see that there's regions kind of, we have a butterfly, and there's regions when the model is quite confident. Maybe this is where most of the, on the left wing is where the most of the negative class is located, and on the right wing it could be a region where most of the positive class is located. And we're going to have some kind of class boundary in between. And model is going to be quite confident in the wings and not confident in the middle. And if we can assume that the model can estimate its confidence correctly, which we can if we do so-called probability calibration. So when you predict something and you use a classification algorithm for that, you tend to get both the predictions, 0, 1, 2, etc. for multi-class, and you also tend to get class probabilities. In scikit-learn, this is just called predict proba method. And interesting thing is that these tend to actually not be probabilities. They are just some numbers that don't actually meet the definition of probability, where you would expect this probability to, in the long run, give you a true incidence of true and false. So if you have a probability of 0.7, you would expect 70% of the data points that are given value 0.7 to be positive. And this is normally not true, but you can calibrate probabilities. I will not go into details here because that's a well-known topic that you can just use implemented solutions in scikit-learn for that. But if you can calibrate probabilities, you can then use them to estimate performance. And how does this work? Basically, it's a very simple idea. If the data points move, or there's more data points that are in the regions of low confidence, the model is going to perform worse. If there's more data points in the regions where the model is very confident, the model is going to perform better. Now let's try to quantify it. So the idea is quite simple again. What we will do is we will take look at every single point in our data set that we're trying to analyze, so say analysis data set, and we will look at the probability. So we're only interested in the model outputs, nothing else. And let's say that this model output is 0.7. Then we know, because we need to have some kind of threshold to decide whether this class, this data point is going to belong to positive or negative class. Let's say that our threshold is 0.5. So then we know that our 0.7 point is a positive prediction. So now it's going to belong to positive predictions. Now the question is it true positive or false positive? Because we know that there is 70% chance that in reality, this point, because we calibrate the probabilities, this point is going to be positive in reality. We know that there is exactly 70% chance that this is going to be a true positive, and 30% chance that this is going to be false positive. And then we're going to create a partial confusion matrix when we will put 0.7 in the true positive cell and 0.3 in the false positive cell. We're going to do it for all the data points in our analysis period. It can be a week, can be a month, can be a day, depending on how much data we have. And we are going to construct these confusion matrices for every single data. and then we'll simply add them up. Once we've done so, what we get is the expected confusion matrix that the model itself expects based on its certainty. And if there's only data drift and there's no concept drift, this is actually true expected performance of the model in the long term. Of course, there's issues with noise in the data, and if we have only, say, 50 data points, this is going to be very unreliable, and real measured performance is probably going to be completely different. But given enough data points, let's say between 300 and 10,000, depending on the class balance and properties of the data set, we will get a reasonably accurate estimation of the performance, even without access to ground truth. So that kind of covers performance estimation. Now we know how it works, and I'll just give you a very quick example of how this actually works. So for the purposes of this presentation, we took the California housing data set, which is data set that probably most of you are familiar with. We turn it into a classification problem, again, just for simplicity, and we used it we trained a simple model, I think, random forest, and then we tried to estimate the performance, estimate specifically log AUC on given chunks of data. And you see here that the estimated and the realized performance follow each other quite nicely. You also see that there is a reference analysis split, and what we mean by that is that the data on the left is something that we will use for calibrating our probabilities to make sure that they actually represent probabilities. So this should be a region when we know everything is working fine. It can be our test data set, could be our validation data set, maybe first month of production, and the analysis data set is the data that we're trying to find out what's going on there, whether the model is performing well or not. So we see that performance estimation can work quite well. Now that we know that our models failed and we can detect silent machine learning failure, let's talk about how to resolve that. And the first step is really to figure out what exactly went wrong, because our model doesn't tell us anything here. It's in a way completely not explainable. So we have to add some kind of explainability here, not on the model level, but on the failure detection level. So it's kind of one level higher. And the way we can do it is really twofold. So first of all, we can look at univariate data detection methods. When we will look at every feature separately, we will not consider relationship between those features, and we will look at our reference data set, for which we know everything is fine, and we'll compare it with the analysis data set. And we're going to run some statistical tests like KS test or chi-square test to see whether the distributions of reference data set and the analysis data set are significantly different. And if they are, then we see that we have some kind of data drift. But this method has few significant or potentially significant shortcomings. The first one is that it does not detect any kind of more complex data drift, or maybe only correlations between model inputs, so correlations between features change. And another one, which tends to be practically more significant and makes these methods almost useless, is if you have 200 features, you will see that things change constantly from the statistical significance perspective. And you will end up with maybe 20 alerts every time you check it, or 10 alerts every time you check it. And at some point, you will get so many alerts that it will become meaningless, and it will not really help you figure out what exactly happened, because everything's changing all the time. So to kind of resolve these issues, we came up with another way of doing that, doing data detection, and that looks at entire model inputs, so entire data set, entire feature set at once. So we can have multivariate data detection, and we're gonna use method that's probably familiar to you if you deal with compression techniques. So what we're gonna do is we're going to train a dimensionality reductor, some form of encoder, or some kind of compressor on our reference data. And this compressor is going to learn, because it needs to be a trainable compressor, a trainable encoder, is going to learn the internal structure of the data, even if it's very complex. Then we're going to run this compressor and decompressor, so encoding and decoding pair, on our analysis dataset. So we take the original data, we project it in the latent space, and then we're going to get it back into our original input space again. So we're going to get reconstructed data. And when it comes to what methods we use, we can basically use anything that compresses the data. So PCA, manifold learning techniques like UMAP, variational autoencoders, anything really works. And to be a bit more specific here, what you need is basically this encoding needs to learn the internal structure of the data, and it needs to reduce the dimensionality. We need to create some kind of compression there, and we need to be able to do an inverse transformation. And there's one more requirement, which is that the latent structure, so this hidden structure that I mentioned, the kind of narrow part of the variational autoencoder, needs to map in a stable way to the original space. And why is that? Because what we're going to measure as our data drift signal is the reconstruction error. So we're going to measure the dislocation of points before and after the reconstruction. So the original points and the reconstructed points. And then we're going to measure it with any distance metric. What we're using is the mean Euclidean distance between the original and the constructed point. So basically the simplest distance metric you could imagine. And then we're going to plot it over time. And what we'll see is that it's not going to start at 0, of course, because there needs to be some kind of loss there. And probably also the internal structure of the data is not learned perfectly, even if lossless compression would somehow be possible. And then we'll see it fluctuate over time. If we see that it stays more or less on the same level, it means that very likely there is no data drift, because the internal structure of the data remains the same. However, if the data reconstruction or the reconstruction error goes up over time, it means that the structure that was learned by the this compressor is no longer relevant, or is no longer the same as it used to be, and the compressor doesn't work as well as before, or the encoder doesn't work as well as before. And on kind of the flip side, if we see that there is a drop in this reconstruction error, it means that the data right now resembles the learned structure even better than before. So we also have data drift, but in kind of opposite direction. You could think of it as data becoming simpler. So we also have data drift. And then we can run it on any subset of features or subsets of data points to get a bit more interpretability. Because if we see that there is, we run it only on 2 features and we see that there is strong spike, we know that the reason for the data drift and the reason for the performance degradation is within these 2 features. So that's basically the reconstruction error, and just simple example here to kind of visualize why it works. Imagine that we have reference data set in blue here and the analysis data set in orange. And you see that there is a these data points are completely different. The data sets are nothing alike. They are actually not translated, but rotated 90 degrees. And if you look at it from one-dimensional perspective over the x-axis and the y-axis, you will actually see that the distributions are almost exactly the same. So univariate data detection will not work here, and will tell you that nothing has changed. It's all exactly the same. But reconstruction error methods will pick up on the difference and will be able to spot that something has gone wrong here. This is, of course, a very simple example and overly exaggerated, but the principle remains the same, that if there is a change in the structure of the features between those features, univariate data detection will not help you there. So wrapping up, let's summarize. So first of all, we need to somehow track performance, and data drift is not the way to do it, because it does not always lead to drop in performance, or even to use a stronger statement, it rarely leads to drop in performance, but we always need to know how to do it, whether it does or not. And secondly, we'd like to just compute performance all the time to know what's going on. But of course, we cannot do it because the production targets are often not available. So we need to estimate performance with our target data, and I presented the technique to do it. And then finally, we should take that and go back then to data detection and try to figure out what is exactly the reason for our drop in performance, so then we can start troubleshooting and resolving any issues. So thanks for listening. As I mentioned already, we are a fully open source Python package. So give it a try, check out our GitHub. If you like what you see there, we would be very happy if you give us a star. We're still a very small library and just getting started. Then also feel free to check the website or add me on LinkedIn if you have any questions. Go ahead and just send me a request. So thank you very much, and that is it.
Thank you very much, and thanks everyone for joining, and we'll see you again next time. Bye.